My question is more addressed to John. So you remarked that in the regime where the corrections to general relativity are extremely small, Frank Wilczek has sanctified the result and told us that we have a proper theory. And the thing that's interesting about it is that there are some predictions already that are perhaps a little surprising. And I'd like to ask about one of them, which is the result that when you look at the bending of, and this is in the Eichenall expansion, of beams of massless bosons, the results depend on which boson you're bending. So I guess the fact that you get corrections to, the standard equivalence principle is not earth-shattering. One thing I couldn't tell, however, was whether or not in the numbers that you quoted, any of these contributed to the classical result, or whether they're all quantum. Okay, they're all quantum corrections. Okay, so why are the numbers different for these different bosons? And a follow-up question is, how high an energy would you have to go to before those differences would be measurable?
So the reason why can be traced to the fact that these are not just local measures of the field propagating through space-time. They're actually, they measure over a range of space-times. And the particles with different spins feel those different ranges, those different points differently. So the tidal effects, they're basically the phrase that I always use is tidal effects, and they're in some sense tidal effects. And tidal effects depend on the composition of the particles. I'm not sure I would have known that ahead of time, but you can see it come out in the calculation.
So I should be thinking then about a beam which is spread out somewhat, and in which you have a distribution of spin which is different for each one of them.
No, actually the limit, the Eichenall limit is trying to make as well defined a beam as you can. But what's different, I mean, it is true that you have to do a wave packet.
Yeah.
But the actual effect is not the wave packet size itself, but the fact that by coupling to the massless particles themselves, so some of the diagrams involve gravitons propagating long distances away. Some of them actually involve the massless particle propagating long distances away. Okay, so it's not itself ever localized. Because it's massless, it can propagate away. So you put a little interaction here, it propagates to here, hits the gravitational field, comes back, and continues on its little merry way. Those diagrams are different for the different particles.
Okay. Were you using a tetrad formulation?
No, I'm using the double copy formulation.
Okay.
Okay, so it's actually done in this more modern technique. It's an extremely painful calculation using old Feynman diagrams. I would never trust myself. There's just too many places for mistakes. But using the double copies, it's not so bad.
Okay, and so the second part of the question was, how high an energy would you have to go to before these effects would be measurable?
How good is your measurement?
With current techniques.
Oh, with current techniques, then you can't measure them at all. But the bending goes like G over R. R squared. And the bending and then around the sun, the R is the distance from the center of the sun in Planck units. Okay. It does, doesn't it?
Any other questions for either Steve or John? I actually have a question for Steve. So if you just think about regular quantum mechanics, so no, Newtonian gravity, don't worry about this, space-time curvature. So your result, that the path integral suppresses a very large class of bad causal sets, but keeps the manifold-like causal sets. Can you relate that in any way to what people do with discrete calculations of path integrals, where, as you mentioned before, that most paths actually cancel out and go away because of destructive interferences? Is this somehow hidden beneath this result? Or do you still have to, once you have a good manifold-like causal set, you still have to then put on top of that the interferences, if you were to do sampling in a discrete way?
I wish I knew the answer to that. I don't. If you're just restricting to manifold-like causal sets, to ones obtained from these sprinklings, then I don't know a way of doing a discrete calculation there, because as Renata said, even for that case, there are way too many. Except it might be possible to take samples. You can, I'll have to think about it. It might be possible to do something discrete by taking samples of sprinklings. Yeah. There are some calculations that are done that way, like figuring out the behavior of dimensions of manifolds when you get to very small sizes. The easy thing to say is that the action in that case is a very good approximation of the Einstein-Hilbert action, so at least the saddle points are the ones we know. Yeah. But beyond that, that's a very good question. I don't know.